Hey there and welcome to another LeetCode video. Today we're going to be doing a problem that I saw today that I thought was quite interesting and I had to look up some solutions for, and then once I figured out the solution I definitely thought it was something really cool, so I wanted to go over this problem today. And so it's going to be problem number 2588, count the number of beautiful subarrays. As you can see, it's a newer problem. It's in one of the recent contests. And so you're given a zero indexed integer array nums. In one operation, you can choose two different indices that are just in the array, and they just have to be different. Choose a non-negative number k such that the kth bit is 1, and I'll explain what this means, and subtract 2 to the k. A subarray is beautiful if it's possible to make all these elements equal to 0 after applying the above operation any number of times. Turn them into beautiful subarrays. Okay, so I'll go over this example, and I'll kind of explain what they mean in the code. Okay, so let's go over this first one, 43124. So basically what they mean is the operation you're allowed to do is if you have two numbers with a 1 in the same index. So for example, if you have this 4 and this 4, so 4 would be this. If you have two numbers with a 1 in the same exact index location for both, then you are allowed to change that to a 0. And you can do this as many times as you want with, whatever numbers you want. And then the result of your subarray has to be that everything equals 0. So for example, so they show you what arrays are valid. For example, for this array, you might think that you can do that. Like at first, what I thought it meant is you're just subtracting a power of 2 from each one, but that's not the case, right? So what you're actually doing from here is you have to subtract from the same index. So like if you have this 4 and this 2, you can't just subtract. You can't subtract 2 from each of them because this 1 is in a different index. And so the two examples that this does work in is they show 312. So for 312, for example, 3 looks like this, 2 looks like this. So they're saying you can subtract a 1 from here and from here, and now what do you get? So this is a 1, this is 0. So now your numbers are 1, 1, 0, and then 1, 1, 0 looks like both like this, so you can subtract a 2 here and a 2 here. And that's what they mean, is you have to take two numbers and you can change a 1 at the same index into a 0. And so let's look at the final example for this 4, 3, this one right here. Okay. And so first of all, so what you can recognize is because 312 is a solution, 43124 is also a solution because for 4, it's just this and this. And so if we get rid of these, now 4 and 4 becomes 0 and 0, and this is our old 312 that we had originally, which also can go down to a 0. So that's kind of what they're saying. But this problem definitely seemed intimidating to me when I first saw it. I was like, well, this might be like some dynamic programming, or like, what am I missing? Like, how do I know in which order? That just seems like there's so many combinations, so many things to try. But the thing you can recognize actually is that, so there's two things you need to know for this problem, and this is going to be the first thing. So the thing you can recognize, for example, let's look at this 312. So they're basically saying take two ones at the same index, and if they're at the same index, change them to a 0. What does that sound like? Take two ones, and if they're at the same position, change that to a 0. What bit operation do we know that does that? And it's actually an XOR, right? So 1 XOR 1 equals 0 because XOR means exclusive OR. So one of these has to be a 0, right? So 0 XOR 0, or 1 XOR 0 equals 1, and then 0 XOR 0 is 0, but 1 XOR 1 is 0. So can we just actually XOR these numbers? And let's see what happens if we try to do that, right? So for this 312, we have 3 and we have 1. So we try to XOR, and I'm just going to do the symbol for the XOR. So what's that going to look like? So we have a 1 and a 1 here, which means XOR of that is 0, and then we have a 1 and a 0, so the XOR of that is 1. So the XOR is going to be 1, 0 here. Now we put in this 2, and we know that an XOR of a number with itself is 0, so it's 0. So that worked. Now let's try this big thing, this 4, 3, 2, 1, 4. And we're just going to go number by number and XOR it. So we have 4 and 3, we XOR. So 1, 1, 1, right? Now we have 3. Or sorry, no, we used 4, we used 3, now we're putting in 1. Okay, so 1 is this. We XOR 0, 1, 1. Okay. Now, make this a little bigger. Now we put in 2. 2 is 1, 0, so 0, 1, 0, XOR 0, 0, 1. And then we have this final thing, and we XOR that with a 4. What's a 4? It's this. XOR, and you get 0, 0, 0. So you can see, actually, for a beautiful subarray, all we really need is just to XOR every single number, and then we're good. So now we know how to calculate a beautiful subarray. Well, how do we actually get all these subarrays? And that's going to be the tricky part. So they're saying return the number of all the subarrays. So let's say, let's just like make this problem, now that we know how to do that, let's say instead of our arrays, we just had ones and zeros, and we simply just had like some count thing, right? Or actually, no, let's not do that. So let's say we do have this 4, 3, 1, 2, 4. It can keep going and going and going and going. And so we can get a subarray by using a left and a right pointer, but how would we know how many subarrays actually have this, right? In order to figure this out right here, and we have a subarray, this would take n time, right? So this would take n time, and then we also have how many subarrays total we have to check. Well, it would be something like 4 all L's, and then we'd have to do 4 all R's. And that would be, this would be n, this would be n, and this would be n, right? So that would be n cubed. And so we actually look at the complexity here. It's actually 10 to the 5th, which means we need something better than n squared. Well, let's say our problem instead wasn't this XOR thing, but it was just like a sum of like, like let's say our problem was literally just, instead of this XOR thing, let's say it was like a sum of numbers, right? So we have this 4, 3, 1, 2, 4. Now instead of this XOR, let's say we're trying to get like all the subarrays that add up to some number. How would we do that? Like how can we save time? So if we have some subarray like this, we know it has to be continuous. So how could we know that this subarray adds up to some number, or this subarray, or whatever? Well, a really easy way to do, I think I did a problem like this before too. A really easy way in big O of 1 to get a sum of an array that you know the indices of is prefix sums. And what prefix sums does is we're calculating the sum at every index. And so if we have the sum, like let's say we have an array like this, right? So we have this 4, 3, 1, 2, 4, and we're trying to get this array. We're trying to get the sum of this array quickly in big O of 1. What prefix sums is going to do is it's going to calculate the sum up to every single element. So like it'll do the sum up to here, 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 and that'll store that in an array, right? So that would look like 4, 7, 8, 10, 14, and so on, right? And so how do we actually get this array? Well, it's actually just the sum up to here minus the sum, if we are including this value, minus the sum up to here, right? So we can easily just do, we're going to have the sums array. We can easily just get the two indices that we want and just subtract the n from the start. So that would be 10, and that is 10. And so that would save us time. And we can actually, turns out, we can do the same thing with XORs. So what we can actually do is if we do have this 4, 3, 1, 2, 4, we can actually store the XORs of all the numbers up to a prefix. And so what would that look like? So that would be like 0, and then it would be, yeah, so you need to store a 0 just because, let's say you're trying to get the sum of this whole thing, then it would need to be this index minus the index before this one, which would be this 0, right? And that makes sense. XOR of no numbers is 0. And so here we would have 0 and 4, and then whatever that is, or sorry, not and, but XOR with 4, whatever that is, and or with 3, whatever that is. Like we'd have a cumulative XOR, right? And so if we wanted some subarray like this, we can just say, okay, well, let's take whatever's here and subtract whatever's here. And we can get that in big O of 1 time. So now that we know that we can get that in big O of 1 time, let's see how that simplifies our work, right? So for our sum, or whatever, like we can actually, it's not really our sum, it's the check if it's a beautiful subarray or not. That's going to be in big O of 1 time now, because we are going to have this prefix sum thing. But we have another problem, right? So even if we do the check in big O of 1 time, that's cool, but we still have to iterate through every single left and every single right, right? Because we still have to get every single subarray, and there's L times R combinations. And so that's a problem because we still need to, we can't do that, right? This is n squared. So how do we get this in something faster? And so let's think about this. They're asking us, what are the beautiful subarrays? Well, what can we do to figure that out? Because for our sums, So our sums do work a little bit differently, right? Like for sums, you can't do this. But let's say our problem was reworded. So let's say instead of sums, we were doing differences, right? And so let's say you had some numbers like this. Let's say you had -10, 0, 0, 0, 10 or something, right? And you want to figure out the same question with this. And so what would our prefix sums look like? Well, it would look like, so you'd have a 0 to start, but then you have -10, -10, -10, -10, 0. And so at every single prefix, you could figure out, well, have I seen this before? And then if I have, that's how many like subarrays you have. Like let's say your goal is literally just to give you an array where the subarray sum is equal to 0, right? So we'd say like, okay, so here, have we seen this before? No, we'd have a count. So let's just have a count here. So let's just say counts. So 0 we're gonna skip. We're gonna initialize our thing to 0 is gonna have a count 1. Now -10, we're gonna say, do we have any -10s? No, we don't. Okay, but let's add it in. 1. Okay, we have another -10. Do we have a -10? Yes, we do. Right? And so that means that we do have a subarray at this point where our subarray is -10. And that is true. So here it would actually be this subarray, right? Because we need to subtract this number here. So that would be that subarray. So let's just say we have a res. So that would be 1. Okay. Now let's try to find the new subarray. Just get rid of this. Okay. So we'd be over here and we ask ourselves, oh, by the way, then we need to also update the count because now we have 2. And so now here we're at this subarray and we need to ask ourselves, have we seen -10? Yes, we have. We've seen it twice. So if we've seen it twice, then we should be able to have 2 subarrays here with this index being then. So do we? Yes, we do. So this is a subarray and this is a subarray, and right, both of these sums are 0. So that's going to be another 2. Okay, so let's update that to 3. Then same thing here, and then this is also updated to 3. Now same thing here. Have you seen it before? Yes, we have. So we should have more subarrays. We should have 3 subarrays in this case. So we have this one, we have this one, and we have this one, right? So that's going to be 6. And now we're here, and we ask ourselves, have you seen the 0? Yes, we have. We've seen it 1 time, so there should be a subarray as well here, and there is 7. And so that's the same thing with this XOR thing. If you've seen something before, the number of times you've seen it is how many subarrays you can have. Because your subarray would just be, like if this was prefix I equals prefix J, then your subarray would be, so I think this prefix is like 1 past the number, right? So if this is 0, 1, 2, 3, 4, 5, and this is actually prefix 4, yeah, then our subarray would be J minus 1, and then I, remember we want the subarray to be, to not include this I value, right? Because this is what we're subtracting. So I think it's going to be 1 greater. So I think this is actually I. So it would be something like this would be our actual subarray in the values. Like if this is R or whatever, R. So that would be kind of like the start and end index of our subarray. So hopefully that makes sense. That's why you need to have a count of how many times you've seen these things before, and that'll tell you how many subarrays you'll have ending with the exact index you're at. So now we have a linear time solution, right? We can get this prefix sums, which is going to be big O of n time, and then we could traverse the prefix sums, and we could just ask yourself at every index, how many times have you seen it before? And the number of times we've seen it before is how many subarrays we have with this prefix sum ending being, you know, the end of the array. And so we just add all that together. So let's code that up. So we're going to have, remember, we're going to have a result. We're going to have a prefix sums. And for our first element, we're going to have it equal to 0, right? Because we need to do the empty array, because like let's say we have a solution like this, then we're going to have the prefix sums at this index minus the prefix sums at the index before this index, which would be the empty array. So prefix sums is going to start with 0, which makes sense. The XOR of an empty array would be 0. Now we need to also have a counts dictionary, so we can keep track of how many times we've seen a prefix sum before. So that's just going to be default dict int. So now for num in nums, we need to add the prefix sum, so we also need a total equals 0. So we need to do total XOR num with it. So this or equal just means XOR the current number to the total and make that the new total. And so that's how we're going to do the prefix. It's not, remember, it's not prefix sums, it's prefix XORs. So that's going to be that. And then we need to just throw that into the prefix sums. So this is pretty prefix sums. Okay, there we go. Why is it? It's weird. Hopefully this is tabbed fine. Okay, and then we just need to do prefix sums. How am I doing? Okay, sums.append total. Okay, so now that we have these prefix sums, we need to go through them, right? Okay, for some reason, yeah, this is all indented wrong. There we go. Okay, so now we need to go through our prefix sums, remember? And then for each prefix sum, we need to ask ourselves, have we seen this before and how many times? And that's what we need to add to the total. So for prefix and prefix sums, then we need to do res plus equals counts prefix. And so if we haven't seen it before, this should just be 0, so that's not going to matter. But then, so we look how many times we've seen it before, and then we need to actually update the count. So let's do that. So counts prefix plus equals 1. We're going to update the count. We're going to turn the res here. Okay. And that's all for that. Okay. So hopefully that makes sense to you. If it's a little complicated, you can, like I said, try numbers that you add and subtract. It might make it easier. Or you can even do, instead of even make it easier, what numbers that you could add and subtract, you can just have like zeros and ones and negative ones. That way you're going to have a lot of repeated, values. Because if you have like 5, 2, whatever, it's hard to get the same stuff. But if you just have zeros, ones, and negative ones, and then you try to do the same thing, subarrays with zeros, ones, and negative ones, and you just like follow this logic with that, it'll make it a lot clearer instead of this XORs, because then you'd have to manually calculate XORs all the time. Okay, so like I said, the time complexity is going to be big O of n because we are just going through the nums and then we're going through the prefix sums. And for space, it's going to be big O of n as well because we're storing the prefix sum for everything in nums. And the most counts can ever be is every single number or every single, like, all these values can technically be unique. And so that would be big O of n as well, where n is the length of nums. Okay, so that's all for this video, and if you liked it, please like and subscribe to the channel, and I'll see you in the next one. Thanks for watching.